So let's do a couple of examples of this. In fact, both a left and a right sum. So when we see this funky symbol here, right, that means for us right now, find the area of the curve underneath the curve. So here's our function, t cubed, and we want to find the area of between t cubed and the x-axis. Let me try that one more time. So t cubed kind of looks like this. So we're looking at 1 to 2, and we're trying to estimate this area. We're going to use a step size of 0.5. So I'm starting at 1 and I'm ending at 2 because that's what these numbers tell me to do. And if I'm doing a step size of 0.5, well, then we're going from 1 to 1.5 to 2. So just for myself over on the side, 1, 1.52. I'm going to make a little table. So here's x or t's, and here's my f of t. So at 1, I'm looking at t cubed, so 1 cubed. My function value is 1. At 1.5, my function value is 1.5 cubed. That's 2.25. And at 2, my function value is 2 cubed, which is 8. So that gives you a little idea about what the points are. Okay, so we're going to look at left endpoints to start with. So since I'm doing this in step sizes of 0.5, we actually have 2 rectangles. So I've got 1 to 1.5, and then I've got 1.5 to 2. Pulling from what we knew from Euler's, then I want the area of those rectangles. I need the height at 1 plus the height at 1.5 times my delta t. My height at 1 is 1, my height at 1.5 is 2.25, which is why I did the little table, and delta t is 0.25, and so that works out to be 1.625. So an estimate for the area under this curve is 1.625. It's an underestimate. Right? The blue sits entirely within the red. My rectangles are entirely within the area underneath the curve, but it gives an estimate. Now, if I wanted to use the right-hand side, the difference is instead of using 1, I'd want to use 1.5, the height at 1.5, for the first rectangle. And then we'll use 2, the height at 2, for the second rectangle. So we get sort of these green rectangles rather than the reds or the blues. We're still doing a step size of 0.5. So I still only have 2 rectangles. Again, I'm just using 1.5 and then 2 to get my function value heights. So f of 1.5 is 2.25. F of 2 is 8. My step size is 0.5. I wrote 0.25 over here. That's 0.5. And so that is equal to 5.125. This one's bigger. Right? Underneath the curve, the red piece would be sit entirely inside the green. We've overestimated at this point. But that gives you an idea how we approach these. The last piece I want to mention is how in the world did this work from Euler's method, which felt really different, to this. And it's really something called the fundamental theorem of calculus. We're not going to do this in depth yet, but if I have this expression, if I let f be this integral, this funny expression, then its derivative gets us back to this piece inside here. There is a relationship between derivatives and antiderivatives. In the case of finding these areas, that relationship is so nice that we don't have to go to the template piece. It's sort of inbuilt. We will spend a lot of time later on working on this relationship, but hopefully the idea of a derivative and an antiderivative, you're like, yes, those two things in fact should be related to each other, and they are. It's a really big deal. We'll do it in depth a little bit later.